Hey everyone, this is Maths Guy channel here, and today we're going to be reviewing differentiation. This is sort of a new topic in mathematical methods, and it's talking about, we may have learned this a bit last year, it's talking about calculus and rate of things such as rate of change, and gradients of functions. So a quick review is that the average rate of change is rise over, so which is kind of like the change in x and y values, so kind of like the gradient, really, the rise over run, and it's shown as f of x minus f of x, f of bracket x plus h minus f of x plus h minus x. So you can think of it as y1 minus y2, or x1 minus x1 minus x2. So x plus h is the x values, f of x plus h is the y value, and etc, etc. And you take the x's out from the bottom, you get f of bracket x plus h, take away f of x, all over h. And the derivative is f dash of x equals the limit of that as x gets closer to 0. We keep in mind that you can't actually ever touch 0 because you can't divide 0 by any. You can't divide anything by 0. As we reviewed in the equation in the function 1 over x, you get two different answers. And it can be, the derivative can be expressed as f dash of x, or dy dx, or d over x, d over d of x, of f of x. Okay. So right now we're going to be going through the derivative of x raised to the n as a polynomial, where n is a z. So where n is z. So like n is a positive rational number. So like 1, 2, 3, the whole numbers, positive whole numbers really. So the rule is if f of x is some coefficient x raised to the n, the derivative f dash of x is n times a times x raised to the power of n minus 1. So you put the power in front of the x, you drop the power by 1, where n is a real number and a is a real number. So if f of x equals g of x plus minus h of x, then f dash of x is the derivative of g plus minus the derivative of h of x. I'm not going to go into a lot of detail of that, but it works out if you try it. Okay, so the gradient function, actually the root of a polynomial. If we take for example x squared, and we see that to the point 1 1 and 3 9. We can think of this as 1 1 as f of x, the x and f of x. And you can think of the second point as x plus h and f of x plus h. So you have your gradient. If I calculate rise over run, so which is 8, so 9 take away 1 over 3 take away 1, so it's 8 over 2. Oh sorry, 4, my bad. So that's your gradient. So the gradient, so the derivative, so if this is x squared, so a is 1, n is 2, this becomes 2 times 1 times x, and the power is 2 minus 1, so it becomes 1. So the derivative of x squared is 2x here, as you can see here. And the first thing you notice is that the x intercept at the turning point of x. So you can see here, at the origin, there's a turning point here. It's when it turns from negative to positive. You can see here that it stops there. So whenever you have a turning point of some kind, that is the derivative at the turning point or stationary point is going to be 0. And you can see like it was 2x here. So the graph is going to be 1 degree lower than f of x. That intuitively that makes sense because here f of x is n and f dash of x derivative, the power is n minus 1, so it's 1 degree lower. Okay, next point, when f of x has a positive gradient, f dash of x is above the x-axis. So x squared here, this part is all positive here. You see that the gradient here is also positive. And if you go here on this side, because it's downwards, so right, I don't know, negative 1, 1, and negative 3, 9. You can see that here, the gradient, if I work out the gradient, it's going to be negative, and on the gradient function, it's going to be negative as well. Well, I didn't really talk about the limits that well, but like, for example, if we go here, if we work out the gradient at x equals 2 here, so we can get x is 1, we can count the gradient from x of 1, x of 3, we can get the gradient there, and as both values approach 2, you approach the correct value of the gradient at that point, and that's kind of how that thing works. A gradient of a function exists where it is smooth and continuous. Sometimes, for example, you have hybrid functions, where you see like certain open and close the dots on the graph. Whenever you have endpoints or that sort of thing, there's not going to be a gradient at that particular point. And tangent drawn f of x equals a for h theta a to exist. So what this is saying is that if you have a graph and you say x equals 2, like here, for 2, 4, what this is saying is that if you can draw a tangent line here, then you can get an answer here. So here, the example at the point 2, x equals 2, the derivative to the gradient is 4. That's what I'm saying. Connect the lines. Okay. And intuitively, that makes sense. Also, equations of tangents and perpendicular lines. Okay. So let's say, for example, we want to calculate the tangent of x equals 2. Like, imagine you have a function that is tangent to this parallel x squared at x equals 2 at this particular point. You want to work out what's the equation of the graph. So first you work out the gradient of at this point, so x equals 2. So you work out here it's going to be 4. So you write f of x equals 4x plus c. It's sort of we'll add a slider for c. That's visual. So you want to go through this point c here. I'll go to the point 2, 4 here. And we can find an answer that matches it. And the answer here is minus 4. You can see that if you do the math, it should work out because it happened. So for the case of x equals 1, x equals 3, the gradient happened to be 4. But as you get closer and closer, it should approach here. So the value of 4 here. So I want to work out the gradient at x equals 3. It's going to be check it 3 here. It's going to be around 6, which makes sense because the power is dropped. Yeah, so that's sort of a visual way of showing how things work. What you want to do for an equation of a tangent, so like you find your gradient and you find a solution that touches a solution for one point here, and that's how you solve that. Okay, so equation of tangent perpendicular lines. So the angle of inclination to the horizontal m is tan theta. So if you have angle. Okay, so the horizontal is sort of the x-axis, the x direction here, and you can see here this sort of angle I made. So like here, this point to the x-axis, that's your angle of inclination. That's measured by m using tan theta. So if you remember your exact triangles, if you have a right angle triangle with sides length 1, 1, that's root 2. The angle is 45 degrees, and since these sides are 1 and 1, the gradient is going to be 45 degrees, and so 45 degrees is a gradient of 1. Helpful note. That particular gradient can be found using -1 over m. So like simultaneous equations. Let's say for example I have 2x and I have f of x equals -1 over 2x. So x. You can see that here they're perpendicular to each other where they have right angles. So it's -1 over m. Horizontal tangent x equals 0. So if you have a constant value, f of x equals 4. The gradient of this function is going to be 0 because you're taking, if you think about it, because it's still, the linear function is still a polynomial with power 1. So when you turn that power down, power becomes 0. Anything 0 is going to be a constant, 1 multiplied by the constant you put in front. So that's how you get an answer. The vertical tangent is undefined. Simply, so if you have a function x equals 2, 4, you can't get a rise over run because the bottom part is going to be 0. You can't divide by 0. That's how you don't get. That's why a vertical tangent is undefined. I know I've talked about a lot of stuff. It looks a bit scary if you haven't done it before. And rest assured, this is sort of an introduction, recapping differentiation. And there's plenty of applications in differentiation that you'll learn very soon. And yeah, that'll be all.